Welcome to this coding walkthrough. In this video, we'll explore LeetCode problem number 46, Permutations. This problem is a classic example of generating all possible arrangements of a given list of distinct integers. We'll break down the problem, discuss potential approaches, and work step by step to implement an efficient solution. Let's dive in. In this problem, we're tasked with generating all possible permutations of a given list of distinct integers. A permutation is an arrangement of all the elements in the list, where the order matters. The output doesn't need to be in any specific order, it just needs to include every unique arrangement. For the input format, we're given a list of integers, where the length of the list can range from 1 to 6 elements, and each element is within the range of -10 to 10. For the output, we need to return a list of lists, where each inner list represents one possible permutation of the input. Let's look at an example to make this clearer. If the input is nums equals 1, 2, 3, we'd need to generate all the different ways to arrange these three numbers. The output for the input nums equals 1, 2, 3 would be a list of 6 permutations: 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. To break this down, we start with one number, say 1, and pair it with the remaining two numbers in every possible order. This results in 1, 2, 3, and 1, 3, 2. Similarly, we can start with the number 2, pairing it with 1 and 3 in different arrangements, giving us 2, 1, 3, and 2, 3, 1. Finally, starting with 3, we generate 3, 1, 2, and 3, 2, 1. Each of these 6 permutations is unique. Now consider another example where the input is nums equals 0, 1. In this case, the input nums equals 0, 1 produces two permutations, 0, 1, and 1, 0. Since there are only two elements, the number of unique arrangements is limited to these two orders. For the smallest possible input, such as nums equals 1, the output would simply be 1, because a single element can only be arranged in one way. The constraints of the problem ensure that the input list will always have between 1 and 6 elements, and every integer will be unique. This means we don't need to handle duplicate elements, which simplifies the problem slightly. With these examples and constraints in mind, let's also consider some edge cases. One edge case is when the input is a single element, like nums equals 5. Here, the output is straightforward, 5. Another interesting case occurs when we include negative numbers, such as nums equals -1, 2. Even with negative values, the process remains the same, and the output would include all possible arrangements, -1, 2, 2, -1. For larger inputs, like nums equals -3, 0, 1, 4, the number of permutations increases significantly, but the approach doesn't change. We need to ensure that every possible ordering is included in the output. By understanding these examples and constraints, we can now approach solving the problem systematically. To solve the problem of generating all possible permutations of a list of distinct integers, we first considered a brute force approach. The idea here is to generate all possible arrangements of the input list and then filter out duplicates. However, since the problem guarantees that the input integers are distinct, this filtering step is unnecessary. Implementing this with nested loops, while straightforward, quickly becomes impractical due to the factorial growth in the number of permutations as the input size increases. This results in a time complexity of n*n, where we not only generate all permutations but also append each one to a result list. The space complexity is similarly n, to store all these permutations. For input sizes larger than 3 or 4 elements, this method becomes computationally infeasible, which is why it is not suitable for our needs. Instead, we chose to focus on the recursive backtracking approach, which is much more efficient for this type of problem. The intuition behind backtracking is that it allows us to explore each potential arrangement of the list step by step. Starting with an empty path, we recursively add elements that haven't been used yet, backtracking whenever necessary. The key idea here is to try placing each unused number into the current path and, once the path contains all the elements, record it as a valid permutation. This is implemented through a helper function that keeps track of the current path and uses an auxiliary array to monitor which numbers have already been included. The time complexity of this approach is n*n, as we construct n. permutations, each requiring O(n) operations to copy the path. The space complexity includes O(n) for storing results and O(n) for the recursion stack. This method strikes a balance between efficiency and clarity, avoiding unnecessary work like duplicate filtering while systematically generating all permutations. Another method we explored is iterative permutation generation, where permutations are created by directly swapping elements in the input array. This approach is based on the same principle as recursive backtracking but avoids recursion by using nested loops or a stack to simulate the process. Elements are swapped in place to form permutations, which eliminates the need for additional recursion stack space. The time complexity, like backtracking, remains O(n), with the same space requirement to store results. However, the auxiliary space can be reduced to O(1) if swaps are done in place without additional data structures. While this approach is efficient, it can be harder to implement and debug compared to recursion. Its added complexity makes it less appealing for this problem, especially given the constraints and the relatively small input size. Ultimately, we chose the recursive backtracking approach as the most suitable solution. It is both simple and efficient, aligning well with the problem's requirements. This approach stands out because it naturally builds permutations step by step, avoiding redundant computations and unnecessary complexity. The key insight is recognizing that backtracking systematically explores all possibilities while leveraging the input constraint of distinct integers to simplify implementation. Although the iterative method is an alternative, its added complexity is not justified for inputs of this size. The brute force method, on the other hand, is impractical due to the factorial growth in permutations. In summary, recursive backtracking provides the best balance of clarity, efficiency, and scalability for this problem, making it the optimal choice for generating permutations within the given constraints. In this problem, we are tasked with generating all possible permutations of a given list of distinct integers. For example, if the input list is 1, 2, 3, we expect an output containing all 6 possible arrangements of these numbers. To achieve this, we'll use a method called backtracking. Backtracking is a systematic way of exploring all potential solutions by incrementally building them and undoing changes when encountering invalid states. This approach ensures we efficiently generate all permutations without redundant computations. The process begins by initializing the input list and a result list to store the permutations. Then, we define a recursive function to handle the exploration and generation of permutations. Let's break this down step by step to understand how it works. The core of the algorithm is the recursive backtracking function. This function takes an index, start, representing the current position in the permutation being built. First, we check the base case. If start equals the length of the list, it means we've formed a complete permutation. At this point, we append a copy of the current arrangement of the list to our result list, ensuring no issues with references during recursion. Next, we iterate through the list, starting from the start index, and swap the current element with each subsequent element to explore new arrangements. After swapping, we recursively call the function with the next index, start plus 1, to continue building the permutation. Once the recursion finishes for a particular branch, we backtrack by undoing the swap, restoring the original state of the list to explore other possibilities. Finally, once all recursive calls complete, the result list contains all valid permutations of the input. Backtracking is effective in this context because it systematically modifies the current state of the input list by swapping elements, explores deeper levels of recursion, and then reverts those changes to ensure no possibilities are missed. Instead of creating new lists for every recursive call, we swap elements directly within the input list. This approach significantly reduces memory usage by avoiding unnecessary copies. Additionally, since the input list contains distinct integers, we don't need extra checks to avoid duplicate permutations. Regarding time complexity, the algorithm generates n permutations for an input list of size n. Copying each permutation into the result list takes O(n) time, leading to an overall complexity of O(n*(n). This method is both efficient and elegant for solving the problem. The key data structures used in this algorithm include the input list nums, which is directly modified to generate permutations, and the result list res, which stores all the valid permutations. Temporary variables are also used during the swapping process to ensure changes can be undone after recursion. The implementation begins by defining the function permute, which initializes the result list and contains the recursive backtracking function definition. The helper function handles both the base case, where permutations are appended to the result list, and the recursive exploration, where elements are swapped and the function is called on the next index. This structure ensures that all permutations are explored and stored efficiently. The function concludes by returning the result list containing all permutations. To use this function, you simply call it with an input list, such as 1, 2, 3, and print the output to verify the results. In this example, the function will generate all 6 permutations of the list, demonstrating the power and efficiency of the backtracking approach. This implementation is compact yet robust, making it a great solution for problems involving permutations of distinct items. This implementation solves LeetCode problem number 46, permutations, using a backtracking approach. The goal is to generate all possible permutations of a list of distinct integers nums. The function permute is defined within a solution class. It initializes a result list to store all permutations and a use list to track which numbers are currently part of the active path. The backtrack function is the core of the solution. It takes 3 parameters. 1. Path, the current permutation being constructed. 2. Used, a Boolean array indicating whether each number in nums has been used in the current recursive path. 3. Res, the list where all valid permutations are stored. #### key steps. 1. Base case, if the length of path equals the length of nums, it means a complete permutation has been formed. This permutation is appended to res. 2. Iteration, for each number in nums, check if it is already used. If not, mark it as used, add it to the current path, and recursively call backtrack. 3. Backtracking, after the recursive call, undo the changes to path and use to explore other possibilities. This ensures that each branch of recursion starts fresh. The used list ensures that each number is included only once per permutation. The backtracking approach systematically explores all valid permutations by adding and removing numbers in the correct order. Finally, the result list containing all permutations is returned. This implementation is efficient, concise, and handles edge cases like an empty input list or a single element gracefully. Here, we start by importing the necessary packages and defining our solution class. The main method of interest is permute, which takes an integer array nums as input and returns a list of all possible permutations. Inside this method, we initialize an empty list called result to store the permutations, and a Boolean array called use to keep track of which numbers have already been included in the current permutation. We then call the helper method backtrack, passing in the input array, an empty list to represent the current path of numbers, the used array, and the result list. Moving into the backtrack method, we see the base case. If the size of the current path matches the length of the input array, it means we have constructed a valid permutation, so we add a copy of the path to the result list. Otherwise, we iterate through each number in the input array using a for loop. If a number has already been used, we skip it to avoid duplicates in the current path. If it hasn't been used, we mark it as used and add it to the path before making a recursive call to continue building the permutation. Once the recursive call completes, we reach the backtracking step. Here, we remove the last number added to the path and mark it as unused in the Boolean array. This step is crucial because it allows us to explore other potential permutations by resetting the state for the next iteration of the loop. The backtracking process ensures that all possible combinations of numbers are explored without repetition. Eventually, after the loop has iterated through all numbers and the recursive calls have fully resolved, the result list will contain all valid permutations of the input array. This implementation efficiently uses recursion and backtracking to systematically generate and collect every possible permutation. We are tasked with finding all permutations of the input array nums equals 1, 2. To do this, we initialize 3 key components: result, an empty list to store our final permutations, used, a list of booleans to track whether each number in nums has been included in the current path, and path, which will hold the numbers as we build each permutation step by step. The process begins by calling the backtrack function with an empty path, an unused state for all numbers, and an empty result. Inside the function, we iterate over nums. Starting at index 0, we add the number 1 to the path and mark it as used. This updates path to 1 and used to true, false. Then, we recursively call backtrack with these updated values to continue building permutations from this state. Now, within the recursive call where path equals 1 and used equals true, false, we again iterate over nums. At index 0, we skip the number 1 since it is already used. Moving to index 1, we add the number 2 to the path and mark it as used. This updates path to 1, 2, and used to true, true. Since the length of path now equals the length of nums, we know we have a complete permutation. We add 1, 2 to the result, which is now 1, 2. After this, we backtrack by removing the last number, 2, from path and marking it as unused. This resets path to 1 and used to true, false, allowing us to explore other potential permutations. In this backtracking step, we return to the state where path equals 1 and used equals true, false. From here, we remove 1 from the path and mark it as unused, resetting path to and used to false, false. Next, we resume iterating over nums, this time at index 1. We add the number 2 to the path and mark it as used. This updates path to 2 and used to false, true. We then recurse again to continue building permutations from this state. Following this process, we eventually generate another valid permutation, 2, 1, which gets added to the result. At the end of this process, the result contains all permutations for the input, 1, 2, 1, 2, 2, 1. For the next example, the input array is nums equals 1, 2, 3. We start with an empty result, an unused state for all numbers in nums, and an empty path. Using the same backtracking approach, we first add 1 to the path and recurse to explore further permutations. Within this branch, we add 2, then 3, eventually reaching a complete permutation, 1, 2, 3, which gets added to the result. After backtracking, we explore additional branches such as 1, 3, 2, 2, 1, 3, 2, 3, 1, and so on. The recursive process ensures that all possible permutations are explored. Once complete, the result contains all 6 permutations of 1, 2, 3, 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Finally, for the simplest case, the input array is nums equals 0. Here, we follow the same backtracking process. Starting with an empty path, we add the only number, 0, to the path and immediately recognize that it forms a complete permutation since the path length matches the length of nums. We add 0 to the result, which now contains 0. Since there are no other numbers to explore, the recursion ends, and the output for this input is simply 0. The time complexity of the permute function is determined by the structure of the backtracking algorithm. First, consider the recursive tree. For an input array of size n, the algorithm generates all possible permutations, which corresponds to n leaves in the tree. This is because there are n choices for the first position, and 1 for the second, and so on, down to 1. Next, at each node in the recursion tree, the algorithm performs operations proportional to O, n. These operations include iterating through the nums array and verifying whether a number has been used. Since there are n leaves and each involves O, n, work, the total time complexity becomes O, n asterisk n. The space complexity of the permute function is influenced by both the recursive call stack and auxiliary structures. First, the recursion depth is equal to the size of the input nums, which means the stack can grow up to O, n. Additionally, the algorithm uses a path list to build permutations, which requires O, n, space, and a used array to track which numbers are included, also taking O, n. However, the most significant contributor is the result list that stores all generated permutations. In the worst case, it holds n permutations, each with n elements, giving it a space requirement of O, n asterisk n. Combining these factors, the overall space complexity is dominated by the result list, resulting in O, n asterisk n. When comparing backtracking to a brute force approach, backtracking demonstrates much greater efficiency. A brute force method would generate all n combinations of the input and then filter out invalid permutations, leading to significant overhead. In contrast, Backtracking focuses only on generating valid permutations by pruning invalid paths early, eliminating unnecessary computation. Mathematically, this ensures that every leaf in the recursion tree corresponds directly to a valid permutation. For best, average, and worst-case scenarios, the algorithm's behavior remains consistent for non-empty inputs since it always generates all n permutations. The time and space complexities, therefore, remain n*n. Across these cases, with the best case being 1 when the input is empty. In summary, the backtracking algorithm achieves a time complexity of n*n and a space complexity of n*n. This efficiency is largely due to the algorithm's ability to prune invalid paths early, focusing solely on generating valid permutations. Compared to brute force, which incurs significant overhead from generating and filtering invalid combinations, backtracking is a much more optimized approach for solving the permutations problem. One common mistake when solving permutation problems is not backtracking properly. For example, during recursion, if you modify data structures like the input list, a temporary path, or a used array, it's crucial to undo those changes before moving to the next branch. Failing to restore the state can result in incorrect or incomplete permutations. Another frequent issue arises when handling non-distinct elements. While this problem assumes distinct integers, if you were to work with inputs like 1, 1, 2, you might end up generating duplicate results unless you add extra logic, such as sorting the input and skipping over duplicates. The base case is another area where mistakes happen. If you add the current path to the results at the wrong recursion level, it can lead to incorrect outputs or unnecessary computations. Make sure you only add to the results when the path length matches the input list. Lastly, improper use of global variables can cause trouble, especially when running multiple test cases on platforms like LeetCode. To avoid unexpected behavior, always initialize or reset global variables properly, or better yet, pass data explicitly as function parameters. Another important consideration is edge cases. For instance, if the input is an empty list or contains just one element, your code could fail or produce unexpected results if these scenarios aren't handled explicitly. Now, let's talk about what interviewers focus on with this problem. Since it's a classic example of backtracking, they'll be looking at how well you understand recursion, state restoration, and pruning unnecessary branches to optimize your solution. While recursion is the most intuitive approach for permutations, showing that you can also solve it iteratively with a stack can highlight your versatility. Efficiency is another key topic to address. Generating all permutations inherently has a time complexity of n, but copying paths into the result set adds an additional n factor, making the total complexity n*n. Lastly, it's helpful to recognize patterns in similar problems, such as generating combinations or subsets, which often share a similar recursive structure with slight variations. Understanding related problems can deepen your grasp of permutations and help you identify shared patterns. For instance, LeetCode number 47, Permutations 2, is a direct extension of this problem, but it handles cases where the input contains duplicate numbers. Next, there's LeetCode number 77, Combinations, which involves generating all combinations of k numbers from a given range. LeetCode number 78, Subsets, asks you to find all subsets of a given list of distinct integers, and it's another problem with similar recursive patterns. Finally, LeetCode number 39, Combination Sum, challenges you to find combinations of numbers that sum to a specific target. All of these problems are great practice for mastering recursion and backtracking techniques, as they explore variations of the same foundational concepts. There are also alternative approaches to solving permutation problems, each with its own trade-offs. The most common is recursive backtracking. This approach systematically explores all possibilities by adding elements to a temporary path and backtracking when necessary. It's intuitive and widely used, but it does require additional space for the recursion stack. Another option is an iterative approach using a stack to simulate recursion. While this avoids recursion stack overhead, it's less intuitive and makes the code more complex. There's also Heap's algorithm, which generates permutations in place by swapping elements. This method is efficient for certain use cases, but it's less straightforward than backtracking. Lastly, many programming languages offer library functions, like Python's itertools.permutations, which can simplify implementation. However, relying on such tools during interviews may not fully demonstrate your understanding of the underlying algorithmic concepts. Each approach has its strengths and weaknesses, so it's important to choose the one that best suits the context of the problem. Great work! In this video, we solved the permutations problem step by step using backtracking. Remember, backtracking is a versatile tool for solving many combinatorial challenges, so mastering it is a valuable skill. Thanks for watching, and don't forget to like, comment, and subscribe for more coding tutorials. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!